Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is composition of linear transformations and their matrices. If you have two linear transformations and they're set up so that you can compose them, what happens to their matrices? That's what the subject of this lecture is. To get started, let me remind you of linear transformations and matrices and the correspondence. So if you have two vector spaces, V and W, and as long as they're finite dimensional, V has dimension n and W has dimension m, and you fix bases for V and W. So S is a basis for V, B is a basis for W. When you want to go from linear transformations to matrices or from matrices to linear transformations, you have to fix your basis once for all. And then for every linear transformation, what we found in a previous lecture, subject of a previous video, was that you can find a matrix that's m by n. It has m rows, m was the dimension of the codomain, and n columns, that's the dimension of the domain. And this matrix does the job of the linear transformation for us. And I will say in a second what that means. Vice versa, if you have a matrix walks through the door, an m by n matrix walks through the door, you can turn that into a linear transformation from V to W, again, using those fixed bases. If the linear transformation corresponds to the matrix A, then what that means, what the purpose of that is that the matrix does the job of the linear transformation for you. And what does that mean? Well, what do you want to do with a linear transformation? You want to take an element of the domain, apply the linear transformation, and get an element of the codomain. So you start with little v in the domain and apply t, and you get t of v. That's what it is here. But t of v, okay, so that's one way to go from v to w via the linear transformation. The other thing you can do is take v, write its coordinates with respect to the basis of the domain. So the coordinates of v with respect to s. That's what this v bracket sub s means. Take the coordinate vector of v with respect to s. So v is a vector in v, but bracket v sub s is a column vector. It's actually an element of Rn, because it's all the scalars you need to write v as in terms of the basis for v. Then you can take that and take a and multiply it by that. And when you do that, a is m by n. This is n by 1, and you get an m by 1 column vector. And if the matrix A is the right matrix, the matrix of that linear transformation, then what you get is not T of V, but you get the coordinates of T of V with respect to B. So you have a choice, either plug V in your linear transformation or find its coordinates with respect to S here, multiplied by A, and get not T of V, but the coordinates of T of V with respect to B. This is how these two things are related, that the matrix does the job of linear transformation for us. We also, the notation we use is that if A is the matrix of the linear transformation, we write the matrix of T with respect to S and B. Even though I write B comma S, I read that as S and B. I say S and B because S is the basis for the domain, and the linear transformation starts with the domain and goes to the codomain. But I write B comma S because of the size of the matrix A, and A has how many rows? As many rows as the size of B. How many columns? As the size of S. Now, if you start with A, if A walked in and you made a linear transformation from that, you can, we call that sometimes L sub A, the linear transformation that came from A. So the point is that if you're sitting there and a matrix walks in, you can make a linear transformation out of that. If a linear transformation walks in, you can make a matrix out of that. Now, for finite dimensional vector spaces, we go back and forth between matrices and linear transformations. You might be working with a linear transformation. It might be fruitful to think of it as a matrix. You might be thinking of a matrix. It might be fruitful to think of it as a linear transformation. And this correspondence is fruitful in both directions. For example, if you're working with a matrix and then turn and think of it as a linear transformation, then all of a sudden you have at your disposal the imagery, the vocabulary, the results about functions. All of a sudden this array of numbers becomes a function, and so we can talk about the domain and the codomain and the image and the kernel and those kinds of things. In fact, I mean, this only works for finite dimensional vector spaces. For infinite dimensional vector spaces, we can't get matrices because those matrices would have to be infinite by infinite. But and for that reason, many mathematicians privilege linear transformations over matrices. Also, when you're talking about linear transformations, you don't have to fix bases. You don't have to be carrying around this extra data of what the bases were for your vector spaces. And so linear transformations provide a basis-free way of thinking about going from one place to another, whereas matrices rely on bases. And so that's one reason, the other reason why so many mathematicians privilege linear transformations over matrices. On the other hand, matrices are far superior when it comes to computations and when you want to actually get things done. Okay, so because of this going back and forth, whenever we see a question, a definition, or a result about either one of them, matrices or linear transformations, we try to translate it to see what does it say about the other one, and whether or not looking at it from the other lens, from the other point of view, helps the matter. So for example, we can compose linear transformations. Not all of them, but if the codomain of the first linear transformation is the same as the domain of the second linear transformation, we can compose those. And so one question we might have is that when you compose linear transformations, what happens to their matrices? So this linear transformation had a matrix, that linear transformation had a matrix, their composition as a matrix. Could I have got that the new matrix from the previous two? That's the subject of this lecture, and in fact, the only subject of this lecture. But before we do that, I need to say to remind you exactly of how we found the matrix of a linear transformation. So you're sitting there, a linear transformation walks through the door. V and W are vector spaces, and they're finite dimensional. Dimension of V is n, dimension of W is m, and you have this linear transformation that you're trying to understand. And so how do we go about finding a matrix for it? Well, if we first find an ordered basis for V, and I need the names of those elements in that basis, so I'm telling you that there are V1 through Vn. I also need a basis for W, but actually I don't need to know what exactly the elements are. I just need to know, I mean, for stating this theorem. For actually doing this, I do need to know what B is. And then the matrix of T with respect to S and B is this mess. I mean, this looks complicated, but it's really not that complicated. It says to find this matrix, you start with the first element of SV1, you apply T to it and send it over. And then when you send it over, you write it in terms of the basis B, and its coordinate vector, this T of V with respect to B, this is a column vector, is an m by 1 column vector. That's the first column. So the first column of this matrix is the coordinate vector of T of V1 with respect to B. You take V1, you send it over, you get T of V1, you write its coordinate with respect to B, you get the first column. Then you go to V2. What's V2? The second element in the basis of the domain. And you send that over and you get T of V2. But that's depending on what W is, T of V2 is an element of W. That's not going to be helpful for you. But its coordinates with respect to B is going to be helpful for you. And that's the second column of this matrix. And you continue that all the way till the end. So you'll have n columns. And each column has m entries because each column is the coordinate vector of a vector in W. And this is the matrix of T with respect to S and B. Again, I say S and B, even though I write B comma S. And the theorem says, well, you can always do this, but so what? The theorem tells you what this does. And this was, again, the subject of a previous video where we proved it rigorously. And so what it does is that this matrix of T with respect to S and B, when you multiply it by the coordinates of any vector in V with respect to S, you get the coordinates of T of V with respect to B. So if you have this matrix, you don't have to anymore remember what T does. If someone gives you a V and says, where does T send this? You say, okay, well, take V, find its coordinate vector with respect to the basis S, then you have a column vector. Take that column vector and multiply it by this matrix, you'll get another column vector. And that column vector is not quite T of V, but very close. It's the coordinate of T of V with respect to B. And this works for every element V in V. In fact, when we prove this theorem, we prove that this matrix that we constructed here is the only matrix that does this, that if you want this property, you have to have this matrix. Because the way we prove this theorem is by first saying that, okay, if this matrix is going to do this job for us for all V and V, it has to do this for the basis elements. And we saw that as long as any matrix wants to have this property, then when you multiply it by the coordinate of a vector, you get the coordinates of the image with respect to the basis of the image of the codomain, then that matrix has to be this. And then what we had to do was to show that, well, this is the only one that could possibly work. Does it actually work for the other V? And we showed that it does. So in other words, if you're looking for this matrix, you're walking down the street and meet a matrix, and you see that that matrix does this, then that means that matrix, when you multiply it by the coordinates of V with respect to S, you always get the coordinates of T of V with respect to B. Then you know that matrix is the matrix of T with respect to S and B. It's not, there can't be some other one also that you could have found. Okay. Now let's talk about the result that we want of this video. So T is a vector space. I mean, T is a linear transformation from the vector space V to the vector space W. L is also a linear transformation from W to U. When you have a linear transformation from V to W and one from W to U, you have an irresistible urge to compose them. And the composition, that means do T then L, we have been calling L circle T. L circle T means do T first and then L, and that's a linear transformation from V to U. Okay, now we need to set bases. So you pick a basis for V, S, a basis for W, B, and we're assuming these are finite dimensional vector spaces. And when you have that, when you have a linear transformation from a finite dimensional vector space to another, and you have fixed bases, as we just discussed, then you have a matrix for that. And let's call that matrix M. So M is the matrix of T with respect to S and B, just the matrix that we talked about on the previous slide. Then we go to L, and we need a basis for U. So now I have a basis for W, B, and a basis for U, R, and L is a linear transformation again between finite dimensional vector spaces. And again, I can define a matrix for that. So N is going to be the matrix of L with respect to B and R. And the question is that, okay, so if I have that, the matrix M and the matrix N, then what is the matrix of L circle T when you compose L and T with respect to S and R? So I have these two matrices M and N. What is the matrix of L circle T with respect to S and R? And the answer is that it's N times M. It's what you get by multiplying the two matrices. You do N times M, and it makes sense that it's N times M and not M times N, because T goes first. So M goes first, then N. And because, and in matrix multiplication, then M is going to be in the right, because when you want to multiply this matrix by a column vector, you multiply M first. Okay, so that's the result. That matrix multiplication corresponds to function composition, composition of linear transformations, and that's sort of neat. Okay. So let's look at an example. So before looking at an example, let's say that if you write this not as just write it out, that means that L circle T with respect to S and R is L with respect to B and R times T with respect to S and B. And in fact, this is a sort of a nice looking function. These notations were sort of cumbersome, but when you write this, it sort of actually sort of makes a little bit of sense. This L circle T got split up in L and T. And then just like matrix multiplication, this B's cancel and we got R and S. So if you look at this, this sort of has a certain amount of elegance to it. Okay, so now let's look at an example. So this time I'm going to pick I'm going to have a linear transformation from R2 to R2. So my domain and the codomain are the same, and therefore I can pick just this one basis for both of them, and I'm going to pick the standard basis V. And then my first map T is 90-degree rotation counterclockwise. So you take every point and we rotate it 90 degrees about the origin. So imagine that that point is sitting on a circle with centered at the origin. You keep it on that circle, just move it 90 degrees over. So that's your first linear transformation. My second linear transformation is reflection about the x-axis. So the x-axis is here. Every point you just reflect it about the x-axis. If it's above the x-axis, just go below the x-axis. If it's below the x-axis, it gets reflected above that. Both of these are linear transformations. Now, the matrix of T with respect to S, when we have the same basis for the domain and the codomain, we don't write the matrix of T with respect to S comma S. We use a shorthand when we write the matrix of T just with respect to S, is this matrix. Why is that? Well, because where did the 0, 1 come from, the first column? Well, you took 1, 0 and see what T does it. If you take the point 1, 0, and if you rotate it 90 degrees, it ends up at the point 0, 1. It was on the x-axis, it goes up to the y-axis and becomes 0, 1. And so that's the first coordinate here. The reason I don't, and because I'm writing things in terms of standard basis, I get 0, 1. I don't have to write it again in terms of the basis because the basis, the standard basis, and 0, 1 is already written in terms of the standard basis. And 0, 1, the point on the y-axis, when you rotate it 90 degrees, it ends up at the point minus 1, 0. And so that's the second column of your matrix. Again, because this is the standard basis, writing these matrices is pretty easy. What about L? The matrix of L with respect to S is also easy. So what is that? So where does 1, 0 go if you reflect about the x-axis? Well, 1, 0 is on the x-axis. If you reflect about the x-axis, it just stays where it is. So 1, 0 goes to 1, 0. Where does 0, 1 go? 0, 1 is on the y-axis. When you reflect it, it just goes right down at the bottom and on the other side and becomes 0, minus 1. Now, what's L circle T? L circle T says rotate 90 degree counterclockwise and then reflect about the x-axis. And that's a linear transformation because it's the composition of two linear transformations. And what our result says, which we haven't proved yet, which we will in a second, is that if you want the matrix of this new composition, rotating 90 degrees, counterclockwise, and then flipping, you just have to multiply these two, the matrix of L times the matrix of T, and you get this. And so this tells you that if you multiply, so we just found the matrix of that. And so, for example, that says that if you take the point 1, 1, what does this new linear transformation does? If you multiply it, you said it gives you minus 1, minus 1. So the point 1, 1 goes, the point 1, 1 goes to the point minus 1, minus 1. While the point minus 1, 1 actually stays fixed. And so actually, if you think about it, this will actually tell you that L circle T is another reflection. It's the reflection about the line y equals negative x. And so this was an example of how if you know the matrices of two linear transformations, you just multiply them and you get the matrix of the composition. And so if you had a lot of things that you were going to do, this matrix multiplication makes your life easier. So let me restate the theorem, and then we will prove it. So this is the composition theorem that we want to prove. And I'm just repeating myself. V, W, and U are finite dimensional vector spaces. S is a basis for V, B is a basis for W, and R is a basis for U. And we have a linear transformation that goes from V to W and another one that goes from W to U. M is the matrix of the first one, T, with respect to S and B, and N is the matrix of the second one with respect to B and R. And then our conclusion is that NM is the matrix of L circle T, the composition of L and T with respect to S and R. And again, if you write this in terms of our notation, it becomes that L circle T with respect to S and R, the matrix of L circle T with respect to S and R is the matrix of L with respect to B and R times the matrix of T with respect to S and B. And if you look at this a little bit, if you pause the video and look at this for a little bit, you will see that it looks sort of nice. Okay, so now let's prove it. So this is the situation that we have. We have V and W, and we have this linear transformation T. We have the basis S and B. S is a basis for V, B is a basis for W. And using S, T, and B, I'm coming up with the matrix M. Then I have L, which is a linear transformation from W to U. And again, using the basis B and R for W and U, I get this matrix N. And then I'm composing those two, and I'm finding L circle T. And what I want is the matrix of L circle T with respect to S and R. So what I'm trying to show is that the matrix of L circle T with respect to S and R is just NM. And how am I going to show that? I'm going to show that by showing you that NM does the job. And as we said, the matrix of a linear transformation is unique. So if you find a matrix that does the job, then that is the right matrix. And so what does doing the right job means? So again, I'm saying that this thing is unique. And so this is what I'm going to do. I'm going to start with what we need to show is that NM does the job. In other words, if you start with a vector V and its coordinate with respect to S, and if you want to find the coordinate of the composition, L circle T at V, which is the same as L of T of V, and find the coordinate of that with respect to R, if you want to go from this coordinate vector to this coordinate vector, then we want to show that NM multiplying by NM does that. If you take NM and multiply it by the coordinate with respect to S, you will get the coordinate of L of T of V with respect to R. If I show that, then I'm done. So the point is that start with this guy. Let's see that if you multiply it by NM, do we get L of T of V, its coordinates with respect to R? So what's the situation? So let's think about it a little bit more. We have V is up in this left-hand corner, is an element of the vector space V, and T sends it to T of V, which is an element of the vector space W. And then L sends that down to L of T of V, which is down here, element of U. Okay, but now I'm going to go to turn this into coordinates and think about coordinates. So if I think about coordinates, instead of V, I have the coordinates of V with respect to S. Instead of T of V, I have the coordinates of T of V with respect to B. And instead of L of T of V, I have the coordinates of that with respect to R. And instead of T, I have M. M does the job for me. So if I take M and multiply it by this coordinate vector, I get that. If I take N and multiply it by that coordinate vector, I get that. But let's see what that means. So M times V of S is T of V with respect to B. So if you take M and multiply it by the coordinate of V, I haven't said anything profound, M and multiply it by the coordinate of V with respect to S, you get T of V beat B. But what about going down here? Well, if you take this now and multiply it by N, you get this guy. And so if you just write that, we say that, well, if you take the coordinate of T of V with respect to B and multiply it by N, you get the result, the coordinate of L of T of V with respect to R. So this is multiplying by M, that's multiplying by N. But T of V with respect to B itself was M times the coordinates of V with respect to S. So if you put that in there, we will see that that's what we got what we wanted. That N times, if instead of the coordinate of T of V with respect to B, we put M times the coordinate of V with respect to S, we get NM times the coordinate of V with respect to S is the coordinate of L of T of V with respect to R, and that's what we wanted to show, and the proof is complete. The idea was that the proof of the pudding is in the eating. We thought that the answer is NM, we multiplied NM by the coordinates of V with respect to S, and we got what we were supposed to. And we knew that there's only one matrix that does that, and so that matrix must be the matrix of L of T, L circle T, which is what we were looking for. Okay, so let's just say what the takeaway from this lecture is. Linear transformations and matrices are two different ways of looking at the same thing. That's the main idea. Whenever you see one, switch to the other. When you see that, switch to this other one. And that change of point of view is helpful. It's always helpful whenever you're thinking of something to have multiple ways of looking at it and not be fixed on your one way of thinking about things. And linear transformations and matrices are two different ways of looking at the same thing. Now, what we showed in this lecture is that function composition corresponds to matrix multiplication. That composing linear transformations is the same as multiplying matrices. Now, you could ask why though. So why am I asking that? I'm asking that because matrix multiplication, actually the definition of matrix multiplication was sort of weird. When you have two matrices and you want to multiply them, if you just put that in front of some random person, they're not going to come up with that definition right away, because the way we defined it was that you take the row of one matrix and multiply it by, find the dot product with this column, and that gives you one entry. Then you take other rows with other columns, and you get, so that was sort of a strange kind of a definition that we came up with. And yet that definition is exactly what corresponds to function composition. And so the question is that, how is that? How did matrix multiplication know, like how was it that this weird definition of matrix multiplication knows that it should correspond to function composition, that works with function composition? Why is that? The fact is that definition of matrix multiplication, even though it was not natural, that it was rigged. It was actually rigged in order to make this theorem true. So we define matrix multiplication in that way so that this theorem is true. This is the most important theorem about matrix multiplication, the fact that it corresponds to composition of linear transformations. Composition of linear transformations is a very natural thing. If you have a function going from here to here and a function from there to there, then composing them is a natural thing to do. Matrix multiplication wasn't, but we defined it in a way to make sure that this theorem is true. In fact, if you go back to the video where we introduced matrix multiplication and look at the examples that we used to motivate why matrix multiplication was defined the way it was, they were all about function compositions. I didn't use that language in those videos because we hadn't talked about linear transformations yet. But if you go and look at them, they were really linear transformations that we were trying to compose and used as motivation for why matrix multiplication is defined the way it is. Also, final point is that the notation, the matrix of T with respect to S and B, is cumbersome. But when we see this relationship with matrix multiplication, then it becomes somewhat satisfying and then sort of makes it worth it. Because it's just sort of nice, like the way it works. I mean, it just seems like it's sort of a natural notation when you look at it this way. This is the end of this lecture. I will see you at the next lecture.